Ready for another deep dive. This time, we're going way back. Like, way back.
Before iPhones, before dinosaurs.
Before Earth even existed.
Exactly. We're talking about the very, very, very beginning of everything. The infant universe.
It's a time period so mysterious, so mind-bogglingly huge and ancient, it makes black holes look like child's play.
And yet we're actually starting to understand it with incredible telescopes and some seriously creative thinking.
That's right. We've got clues scattered across billions of light years, like cosmic breadcrumbs leading back to the Big Bang.
And one of the biggest clues of all is something called cosmic inflation. Imagine this. The universe, just a tiny fraction of a second old.
Like, way less than a blink of an eye old.
Exactly. And in that instant, it explodes in size.
Not just expands, but explodes, like a cosmic firework going off.
Bigger, faster, more extreme than anything we can really wrap our heads around. That's inflation. And it helps explain some of the biggest puzzles about our universe. Like, why does space look so incredibly uniform on the largest scales?
Right. It's like, if you zoomed out far enough, you'd think the entire universe was made in the same cosmic bakery. Everything just seems so evenly spread out. It's almost too neat, if you know what I mean.
Exactly. And that's where inflation comes in. It's like the universe's way of smoothing things over. Think of it like this. Imagine you blow up a balloon really, really fast.
Okay, got it. I used to love doing that as a kid.
So any little imperfections on the surface of the balloon, any wrinkles or bumps, they get stretched out as the balloon inflates.
I see what you're saying. So inflation is like the universe's way of ironing out any wrinkles from its explosive birth.
You got it. Except, instead of wrinkles, we're talking about things like energy and matter. Inflation helps explain how they got so evenly distributed across the vastness of space.
Okay, that's pretty cool. But there's a twist, right?
Yeah.
I've heard rumors that there isn't just one theory of inflation, but hundreds.
That's right. Welcome to the wild world of cosmology. You see, there are over 200 models of cosmic inflation floating around.
200? Seriously? That's a lot of options. So how do we know which one is right? How do we even begin to narrow it down?
That's the million-dollar question, or, in the case of cosmology, maybe the Nobel Prize-winning question. It's one of the biggest challenges in the field. You see, each model of inflation makes slightly different predictions about what we should see in the universe today.
So it's like having 200 suspects at a cosmic crime scene.
That's a great analogy. We're basically playing cosmic detective, looking for clues that can help us eliminate some of the suspects and zero in on the most likely culprit.
And I bet things get even more complicated when you factor in the Nobel Prize. Isn't there a lot of pressure to be the first to solve these cosmic mysteries?
Oh, absolutely. And that can sometimes lead to, shall we say, premature celebrations. Remember the BICF2 experiment a few years back?
Vaguely. Refresh my memory.
Well, this team of scientists announced with great fanfare that they had detected a specific pattern in the cosmic microwave background radiation, basically the afterglow of the Big Bang, a pattern that would have been a smoking gun for inflation.
So they thought they'd found the proof everyone was looking for.
Exactly. The problem was, what they were seeing wasn't actually a signal from the early universe. It turned out to be interference from dust within our own galaxy.
Oh, no. Talk about an anticlimactic ending. So even with the most advanced technology, it's easy to get things wrong.
That's right. It's a humbling reminder that we're dealing with signals from billions of years ago, faint whispers from the edge of time and space.
So how do we even begin to study something as elusive as the very first moments of the universe? What clues are we looking for?
Well, one of our most important tools is something called the cosmic microwave background radiation, often shortened to CMB. Imagine a baby picture of the universe taken when it was just 380,000 years old.
We have a baby picture of the universe. That's
Yeah.
incredible. What does it look like?
Well, it's not something we can see with our eyes. It's a faint glow of microwave radiation that permeates all of space, kind of like a cosmic background hum.
Okay, so we need special telescopes to even detect it.
Exactly. But what's amazing is that the CMB isn't perfectly smooth. It has these tiny temperature fluctuations, variations on the order of 1 part in 100,000.
1 part in 100,000. That's incredibly tiny. Why are those variations so important?
Those tiny fluctuations hold the secrets to how galaxies formed. You see, those slightly denser regions in the early universe acted like seeds, drawing in more and more matter through gravity over billions of years. Eventually, those clumps of matter grew large enough to form the stars, galaxies, and galaxy clusters that we see today.
Wow, so by studying these incredibly faint temperature differences in the CMB, we can actually trace back the origins of structures that are billions of light years across.
Exactly. It's like finding a fingerprint at a cosmic crime scene. By analyzing the pattern of those fluctuations, we can learn an incredible amount about the universe's early moments, its composition, its temperature, and the forces that shaped its evolution.
It makes you realize how interconnected everything is, how events that happened billions of years ago continue to affect the universe we see around us today.
Absolutely. And it's that interconnectedness, that grand narrative that unfolds across billions of years that makes cosmology so captivating.
It's amazing to think that we can look back billions of years and see the seeds of our own galaxy, all thanks to this faint glow of microwave radiation. But I gotta ask, to actually see these temperature fluctuations in the CMB, what are we using? It's not like we're just pointing our backyard telescopes at the sky, are we?
Not quite, though backyard telescopes are cool too. We're talking about some seriously sophisticated instruments here, both in space and here on Earth. Actually, some of the most exciting work is happening right now in the Atacama Desert.
The Atacama Desert, you mean that super dry place in Chile? It's like the last place I'd think of for high-powered astronomy.
Exactly. It might seem counterintuitive, but being super dry and at a high altitude, it's almost like being in space already. Less atmosphere to mess with the observations, and that's where the Simons Observatory comes in.
Simons Observatory. Okay, I'm getting flashbacks to high school physics. Can we get the layman's explanation? What makes this observatory so special?
Think of it like this. It's a giant, super sensitive radio, but instead of picking up music, it's tuned to the faintest whispers of the Big Bang. We're talking over 10,000 detectors, all cooled down to almost absolute zero to pick up those signals.
10,000 detectors. That's insane. Are we sure that's not overkill? What kind of information are they hoping to find with that kind of firepower?
Trust me, when you're trying to pick up a signal from billions of years ago, it's not overkill. It's like trying to hear a pin drop during a hurricane. The Simons Observatory is looking for clues about something called the polarization of the CMB.
Polarization, right. Now we're really going back to high school physics.
Yeah.
I need a refresher here.
Think of it like this. Imagine light waves as being, say, waves on a string. They can vibrate up and down, side to side, all directions. Polarization basically tells us which way those waves are wiggling. And what's cool is that gravitational waves, those ripples in spacetime we talked about, they can actually twist and distort that polarization as they travel through the universe.
So it's like gravitational waves leave their fingerprints on the light itself. And by studying those fingerprints, we could maybe finally get confirmation of inflation.
Bingo! That's the holy grail, anyway. But remember, we're talking incredibly faint signals here. It's like trying to find a specific grain of sand on all the beaches of the world.
Man, it makes you appreciate the dedication and ingenuity of these scientists. Talk about a cosmic needle in a haystack.
No kidding. And speaking of mysteries, there's another layer to this whole story that we haven't even touched on yet. The fact that the vast majority of the universe is made up of stuff we can't even see.
Wait, what? You mean like invisible stuff? Like actually invisible?
You got it. We call them dark matter and dark energy.
Dark matter, dark energy. Okay, those sound like topics for a whole other deep dive. But give me the quick version. What are they?
Well, we know that dark matter doesn't interact with light, hence the name dark. But we know it's out there because we can see its gravity affecting the stuff we can see. It's like there's this whole invisible scaffolding holding the universe together.
Okay, so that's dark matter. Spooky scaffolding. Got it. What about dark energy? Is that spooky too?
Even spookier, dark energy is this mysterious force that seems to be pushing everything in the universe apart. And not just pushing, but accelerating the expansion.
Hold on. The universe isn't just expanding, it's expanding faster. That's kind of terrifying, to be honest.
Yeah, it's a real head-scratcher.
Hmm.
And the scariest part, we have absolutely no idea what it actually is. It's like the ultimate cosmic mystery.
So we've got inflation, CMB, dark matter, dark energy. It feels like the more we learn about the universe, the more questions we end up with.
That's the beauty of it, isn't it? It's a never-ending puzzle, and we're just starting to put the pieces together.
It's mind-blowing, really. All this invisible stuff shaping the universe makes our everyday problems seem kind of small.
It really puts things in perspective, right? We're just this tiny part of something so much bigger and more complex than we can imagine.
Definitely puts a new spin on. The universe is your oyster.
Ah.
So where do we go from here? We've talked about inflation, dark matter, dark energy. Are those the big mysteries cosmologists are trying to crack right now?
Those are some big ones, for sure. Think about those gravitational waves. Finding those would be huge, like finding a signed confession at the scene of the cosmic crime.
Right. But even if we found those, wouldn't there still be a ton of unanswered questions? Like what dark matter and dark energy actually are?
Absolutely. We see the effects, but nailing down what they're made of, what their properties are,
Right.
that's the next frontier. Could be particles, could be some kind of energy field, could be something we haven't even imagined yet.
That's both exciting and kind of terrifying. Like, what if we're never able to figure it out?
I don't think that's the right way to look at it. Every discovery leads to new questions, and that's okay. It's what keeps cosmology moving forward. It's not just about the answers, it's about the journey, the constant exploration.
It makes you realize how much is still out there, just waiting to be discovered.
Hmm.
And honestly, it's a bit overwhelming. Like, how can we possibly keep up with all this?
Well, you don't need to be a rocket scientist to appreciate the mysteries of the universe. There are so many great resources out there. Books, websites, podcasts like this one, even citizen science projects.
Oh, yeah. The citizen science stuff is amazing. You can actually help analyze real data, contribute to actual scientific discoveries.
Exactly. It's a great way to get involved, to feel like you're a part of something bigger. And who knows, maybe you'll even make the next big breakthrough.
I like those odds. Okay, one last question before we wrap things up. We've talked a lot about the cosmic microwave background, that baby picture of the universe. Let's say we could hop in a spaceship, zoom billions of light years away, and look at the CMB from another galaxy. What would we see?
Ah, that's a great question. It gets to the heart of how we understand the universe. We tend to think of ourselves as being at the center, but really, we're just one tiny point in this vast cosmic web.
So would the CMB look different from a different galaxy?
It would. Remember, the CMB is light that's been traveling for over 13 billion years. So if we could view it from a different location, we'd be seeing light that has traveled a different path, interacted with different structures along the way.
It's like everyone gets their own unique view of the early universe.
Exactly. It's a reminder that there are countless perspectives out there, countless ways of understanding the cosmos. And the more we explore, the more we realize how much more there is to learn.
It's humbling, isn't it? To think about the sheer scale of it all. Makes our everyday worries seem pretty insignificant.
It really does. And I think that's a good thing. It's a reminder to stay curious, to keep asking questions, and to never lose our sense of wonder.
Well said. Well, on that note, I think we'll wrap up this deep dive into the infant universe.
Thanks for joining us.
Until next time, keep looking up.
Mm.
And remember, the universe is full of surprises.